Hello everyone. Laith, Henrique, and I will be discussing the used car regression analysis we constructed for our project, covering every major step from forming our problem statement to our modeling and results, as well as answering any questions you guys may have. With that in mind, we will go ahead and get started. To kick things off, it would be best to explain the problem we aim to solve with our project. Before we began, all three of us knew that the problem we wanted to tackle had to be one that was something that we all experienced at some point in the past, and ultimately, the problem we believed that we can attempt to solve was trying to predict what a used vehicle's price should be. All three of us had bought a used vehicle before, and in those scenarios, each one of us bought a used car at a price that should have been way less than what it was sold for. So we thought, why not try to predict what a used car's price should be given based on its current state and depreciation. We also chose this problem because of the business value associated with it. From our own research, the number of used vehicle drivers is double the number of new vehicle drivers. So beyond us three, there are millions of used vehicle owners, buyers, and sellers that struggle to find an equitable price for a vehicle based on different variables such as mileage, manufacturer, and year. The basis for our research question then was to provide the backbone for employing a predictive model which would address the problem we mentioned earlier about used vehicle buyers and sellers identifying a fair price for the depreciation on an automobile without having to be overcharged or undercharged. Therefore, the research question we came up was, how can the price of a used vehicle be predicted based on one and/or more of its features? Our project's data source was gathered from Kaggle and can be found on Kaggle just by searching for Craigslist car data. The dataset is about used automobile entries from the United States on Craigslist and includes relevant information people usually see when they're browsing for a used car, such as price, condition, manufacturer, etc. Initially, the data source contained about 500,000 observations and 25 variables, with each observation representing a used car. The variables represent information about the cars, such as manufacturer, year, mileage, and more. The dependent variable utilized in the regression analysis is price because, as we mentioned earlier, we were interested in predicting the price of a used car based on one or more of its features.
In order to prepare our dataset for the exploratory data analysis phase, there were some data cleaning steps that needed to be performed. What we first did is we removed 11 variables from our dataset, like ID, URL to the website, just any columns that weren't adding any relevant information to our research. We then dropped any rows that contained null values in any of the remaining columns. And this actually resulted in our dataset decreasing in size from 500,000 observations to 100,000 observations. The last thing we did is we removed any cars that had a price greater than $70,000. And you might be wondering, why? And the reason why was most people were buying cars around $9,000, and that was where the median lied. But due to some expensive cars that were considered outliers that were worth up to $3.6 million, cars like Ferraris and Lamborghinis, their prices were so high that they actually skewed our mean to $54,000, making our histogram look very odd. What these numbers are implying is that the average price a person spends on a car is around $54,000 to $55,000. From common sense and just the world that we live in today, we know that that's not true. Once we removed these outliers, we were actually able to get a much more reasonable histogram. Our mean price became $11,000 and our median became $8,500. The histogram is still skewed to the right, however, it just seems more interpretable. Our next step was to analyze some more granular details about these cars. So the first aspect we decided to take a look at was the cylinders of the cars. As we can see from the graph, there are a range of cylinders from 4 to 10. And as we commonly know, 4 cylinders tend to be fuel-efficient cars, while trucks tend to have 6 to 8 cylinders and sometimes even 10. What we learned from the graph, though, is that Ford produces the largest amount of 8-cylinder cars. And we also learned that there is an immense amount of 6-cylinder cars, even more than 4-cylinder cars. The next aspect we decided to take a look at was the manufacturers based on the type of fuel the car intakes. As shown from the graph, most used cars within the dataset intake gas for fuel, which is what we all know in the current state of today. But what's also interesting to see is the manufacturers that produce the most gas cars surprisingly produce a substantial amount of diesel cars and trucks. As we can see, there's a huge landslide for Ford and Chevrolet as they have a huge market share in both gas and diesel cars. Following the analysis from the previous graph, we wanted to see if there was any relationship between gas cars and diesel cars with our dependent variable price, based on visual analysis and observation. We did this visual analysis along with the variable of odometer, also known as mileage, since most people like to refer to mileage when it pertains to the price of a car. As shown in the graph, there is a negative relationship between odometer and price, and it looks pretty linear. This means that as a used car mileage increases, the price of the car decreases. And we typically know this in the world. But what's more interesting to see is that a good amount of time, gas vehicles have the same selling price for a lower mileage compared to diesel vehicles. In other words, this graph is basically showing that diesel cars have a better reselling price than gas cars at any equal mileage.
After doing the exploratory data analysis, we concluded that regression would be the best technique to analyze and predict the price of the used cars in our dataset. We started off with a linear regression, then we ran a step forward, step backward, and step forward backward in order to find the best coefficients to include in the model. We repeated the same process in a polynomial regression. We created 4 B-splines models with 3, 4, 6, and 9 splines. And lastly, we created a smoothing splines model. We did not include more complex models because of the parsimony principle. We figured that in order for these two to add substantial business value, our model needed to be simple, remarkably fast in making predictions, and not take much computing power. Our first model, the linear regression, ended up with 152 coefficients. Most independent variables were statistically significant, and our adjusted R-squared was 68.18%, which is not bad for a linear model. The root mean squared error was 4,711, and the mean absolute percent error was 60.77%, which is huge. We also got the information criteria for the model, and it's also important to mention that the step forward, backward, and forward, backward selections ended up not changing the number of coefficients in the model. Then we created a polynomial regression. The polynomial regression had 154 coefficients. Most of the variables were also statistically significant, but our adjusted R-squared was almost 95.1%, which is outstanding for such a simple regression model. The root mean squared error was 1,832, and the mean absolute percent error was 27.8%, which is way lower than our previous linear regression model. We also got the information criteria, and the step forward, backward, and forward, backward selection ended up not changing the number of coefficients in the model as well. In this visualization, we can observe that the polynomial regression did really, really well in predicting the independent variable. We can see that there's a clear curvature to the data, and even though there's a larger variance in the lower price ranges, as the prices go up, our model gets increasingly precise. I would also say that something much more precise than that would be actually overfitting. This model did really well. The only thing that I would mention is that this model predicted some negative prices, which is a problem. But other than that, I think it would be hard to find a model that would be so simple and would end up with such good results. Here I have a quick overview of the B-splines models that we have created. But overall, they were not really good. The adjusted R-squared were always around 27%, which is nothing compared to our 95% adjusted R-squared for the polynomial regression. And our mean absolute percent error was also like up to the 95%. So they were not really good models anyway. Lastly, we have the smoothing splines regression. Even though the model was good, it didn't capture the whole variance in the dependent variable. So because there's a lot of variance in this black area here, and the best fitting line, even though it's the best possible fitting line, that's yielded by the smoothing splines regression, it does not capture the whole picture of what's going on with the dependent variable. So we decided not to move forward with this regression as well. So in conclusion, we decided to move forward with our polynomial regression model. It was an outstanding model overall, with an adjusted R-squared of 95.1%. It means that 95% of the variance in the dependent variable can be explained by the independent variables. The used car industry is a multi-billion-dollar one, and making a quick buy or sell decision can represent a huge competitive advantage in this market. A simple, fast, and accurate prediction tool will be a valuable asset for firms working in this industry, and we firmly believe that our polynomial regression model can provide real price expectations for virtually every car in the US market and return a dollar amount in just a few seconds. So imagine a scenario where you have a customer coming into your store and asking for $3,000 for you to take his car. If you enter the specifics of the car into the model, it will return to you a $4,000 worth of price. You can be confident that you can purchase the car for $3,000 and you will be able to resell it for something close to $4,000 later on. So this model could help used car resellers to save millions of dollars every year by helping them make good database decisions. So thank you very much for your attention. I hope you enjoyed this presentation, and we're very confident that that our regression model can add substantial value to this industry and to society as a whole.